Good evening, everyone. Tonight we're going to talk about a man who did something absolutely remarkable with nothing more than a stick, a well, some basic geometry, and an assumption that would make most people say, "You're going to bet what on that?" His name was Eratosthenes, and around 2,240 years ago, he measured the entire circumference of the Earth with an accuracy that would make modern surveyors weep with envy. And he did it without a GPS, without a satellite, without even a decent calculator. Just pure, beautiful mathematics and one of the most elegant experiments in the history of science. But here's the thing about Eratosthenes. He was so accomplished at so many different things that his contemporaries gave him a nickname that sounds like a compliment but was actually a bit of a burn. They called him Beta, the second letter of the Greek alphabet. Not because he was second-rate, but because he was supposedly second best at everything. Second best poet, second best mathematician, second best geographer, second best athlete. It's like being called the silver medal guy. Imagine that on your business card. Yet this second best man did something that absolutely no one else had done before. He figured out how big our planet is using nothing but his brain and some shadows. So maybe being second best at everything is actually better than being first best at just one thing. Or maybe his peers were just jealous. We'll explore that tonight. Over the next hour and a half or so, we're going to journey through the life of this fascinating polymath, understand his world, marvel at his method, and appreciate why his legacy still matters today. So settle in and let's travel back to the ancient Mediterranean, to a time when the greatest library in the world stood in Egypt, when scholars debated under columned porticos, and when one brilliant mind looked at shadows and saw the cosmos. Chapter 1. The World Before Eratosthenes. To appreciate what Eratosthenes accomplished, we need to understand what people believed about the Earth before him. And let me tell you, the ancient world had some theories. Now, contrary to popular belief, educated people in the ancient Mediterranean didn't think the Earth was flat. That's a myth that somehow got attached to the ancient world, probably because it makes us feel smarter by comparison. No, the Greeks had figured out the Earth was round well before Eratosthenes came along. Pythagoras, around 550, before the Common Era, had suggested it based on philosophical grounds. Circles and spheres were perfect shapes, so obviously the Earth must be spherical. Very Greek logic. It's pretty, therefore it must be true. But Aristotle, around 350, before the Common Era, actually provided evidence. He pointed out that during a lunar eclipse, the Earth's shadow on the moon is always circular, and the only shape that casts a circular shadow from every angle is a sphere. He also noted that different constellations are visible when you travel north or south, and that ships disappear hull first over the horizon. These weren't just philosophical musings. These were observations anyone could verify. The Greeks were excellent observers. So, by the time Eratosthenes came around, we're talking about 276 to 194. Before the Common Era, roughly the spherical Earth was established knowledge among the educated elite. The question wasn't the shape, the question was the size. Some people thought the Earth was relatively small, others thought it was enormous. Aristotle had taken a stab at it and suggested a circumference of about 400,000 stadia. Now, a stadion, that's the singular of stadia, was a Greek unit of measurement. And here's where things get complicated. There were different kinds of stadia. It's like if you asked someone how many feet something is, but some people are using their actual feet, and others are using a standardized foot measurement, and nobody's quite clear which is which. The exact length of Aristotle's stadion is debated, but his estimate translated to something much larger than the Earth actually is. The point is, people were guessing. They were making educated guesses, sure, but guesses nonetheless. What the ancient world needed was someone who could actually measure the Earth. Not estimate based on philosophy or rough calculations, but really truly figure it out with reproducible methodology. Enter our hero, Eratosthenes of Cyrene. Now, Cyrene, modern-day Libya, was an important Greek colony on the North African coast. It was a wealthy city, famous for its silphium plant, which was used for everything from seasoning food to birth control, and was so valuable that it may have been harvested to extinction. That should tell you something about Cyrene. It was a place where money and trade and culture all mixed together, a cosmopolitan city on the edge of the Mediterranean. Eratosthenes was born here around 276 before the Common Era, into a world that was rapidly changing. Alexander the Great had died just 50 years earlier, and his empire had been carved up among his generals. Egypt fell to Ptolemy, one of Alexander's companions, who established the Ptolemaic dynasty. And Ptolemy had big plans for his capital, Alexandria. Alexandria was designed to be the jewel of the Mediterranean, and at its heart was the Great Library, or more accurately, the Mauseon, the museum, which included the library. This wasn't a museum in our modern sense with dinosaur bones and paintings behind glass. The Mauseon was a research institution, a university, a think tank, all rolled into one. Scholars lived there, worked there, debated there. It was like if you took Princeton, the Library of Congress, and the Institute for Advanced Study and merged them into one institution with essentially unlimited funding. And the library, oh, the library. Every ship that docked in Alexandria was required to hand over any books it carried so they could be copied for the library's collection. They were supposed to return the originals and keep the copies, but there are stories of them returning the copies and keeping the originals. The Ptolemies were serious about collecting knowledge. At its height, the library supposedly contained somewhere between 400,000 and 1 million scrolls. It was the center of learning for the entire Mediterranean world. This was the intellectual atmosphere into which young Eratosthenes arrived. He had studied in Athens first because of course he had. That's where you went if you were a serious scholar. He studied philosophy under Aristo of Chios, a student of Zeno of Citium, who founded Stoicism. He studied poetry and theater. He was, by all accounts, brilliant at everything he touched. Not the absolute best, remember that beta nickname, but brilliant nonetheless. And then, around 245 before the Common Era, when he was about 30 years old, he received an invitation that would change his life. Ptolemy III Orgetes wanted him to come to Alexandria to tutor his son and to become the third head librarian of the Great Library. Let that sink in for a moment. The head librarian of the Great Library of Alexandria. This wasn't just a job. This was one of the most prestigious intellectual positions in the ancient world. You had access to all of human knowledge. As it existed at that time, you had funding. You had brilliant colleagues. You had the ear of the king, and Eratosthenes said yes. Chapter 2. Life in Alexandria. Picture Alexandria in the middle of the 3rd century, before the Common Era. The city is maybe 100 years old, built on Alexander the Great's ambitions and Ptolemy's gold. The streets are laid out in a grid very modern, very organized. The harbor is dominated by the Pharos, the lighthouse, one of the 7 wonders of the ancient world, standing over 100 meters tall and guiding ships home with its fire beacon at night. The city is a melting pot. Greeks, Egyptians, Jews, traders from Arabia and India and Ethiopia, everyone comes to Alexandria because Alexandria is where things happen. Ideas, goods, cultures, they all flow through this city. You can hear a dozen languages in the marketplace. You can sample foods from across the known world. And if you're a scholar, you can walk into the Mauseon and discuss philosophy with the smartest people alive. This is Eratosthenes' new home, and he thrives here. As head librarian, his responsibilities are enormous. He has to maintain the collection, acquire new works, supervise the copying of scrolls. Remember, every book had to be copied by hand, which means every book was expensive and every copy was a major investment. He has to manage scholars, settle disputes about the authenticity of texts, and catalog everything. Ancient librarians didn't just shelve books. They were like the Google of their day, the keepers of all searchable knowledge. But Eratosthenes isn't content to just manage. He's a researcher at heart, and Alexandria gives him the resources to pursue whatever interests him. And Eratosthenes is interested in everything. He writes poetry, a piece called Hermes, that was apparently quite good. He writes literary criticism and works on chronology, trying to figure out when historical events actually happened. This is harder than it sounds in a world where different cities use different calendars and dating systems. He writes Geographica, a comprehensive work on geography that becomes the foundation for all later Greek and Roman geography. In fact, he's the one who coined the term geography, geo for earth, graphane for writing or description. He literally named the field. He works on mathematics, contributing to number theory and geometry. He invents the sieve of Eratosthenes, an algorithm for finding prime numbers that's still taught today. You list all the numbers, strike out the multiples of 2, then the multiples of 3, then 5, then 7, and what you're left with are primes. Simple, elegant, effective. Very Eratosthenes. He writes about ethics and philosophy. He studies astronomy. He makes a star catalog. He calculates the tilt of the Earth's axis, what we call the obliquity of the ecliptic, with remarkable accuracy. And somewhere in all of this, he hears about a well. Now, this is the moment where the story usually goes. Eratosthenes heard about a well in Cyrene, where, at noon on the summer solstice, the sun shone straight down to the bottom, and this gave him an idea. Which is true as far as it goes, but it makes it sound like he just stumbled upon this information randomly, like finding a $20 bill on the sidewalk. The reality is almost certainly more interesting. Eratosthenes is the head of the great library. He has access to reports from all over the Ptolemaic kingdom and beyond. He's reading everything: travelers' accounts, military surveys, merchants' logs, astronomical observations from different cities. He's looking for patterns, for data points, for interesting anomalies. And he comes across reports from Cyrene, modern-day Aswan, about 5,000 stadia south of Alexandria, that on the summer solstice, at noon, the sun is directly overhead, perfectly vertical. People notice this because wells don't have shadows in them at that moment. Obelisks don't cast shadows. If you stand up straight, your shadow disappears. Now, this doesn't happen in Alexandria. In Alexandria, even at noon on the summer solstice, vertical objects cast shadows. Not long shadows, the sun is high in the sky, but definite shadows. And Eratosthenes, brilliant polymath that he is, realizes this is measurable. This difference in shadow angle is information. And if you make one simple assumption that the sun is very, very far away, so far that its rays hit the Earth essentially parallel, then this information tells you something profound. It tells you the curvature of the Earth. Chapter 3. The Method. Let's talk about Eratosthenes' method, because it's genuinely one of the most beautiful pieces of reasoning in the history of science. Imagine you're standing on a ball, a big ball, but a ball nonetheless. Now imagine the sun is so far away that by the time its light reaches you, all the rays are traveling in the same direction, parallel to each other. This is actually true. The sun is about 150 million kilometers away, so its rays are indeed essentially parallel when they reach Earth. Now, if the Earth were flat, those parallel rays would hit everywhere at the same angle. A vertical stick in Alexandria would cast the same shadow as a vertical stick in Cyrene. Everything would experience noon at the same time, and shadows would be the same length everywhere. But the Earth isn't flat. It's curved. So when those parallel rays hit the Earth, they strike different locations at different angles. Picture it this way. Take a orange, yes, we're using an orange as the Earth. Bear with me and shine a flashlight on it from far away. If you stick two toothpicks in the orange at different points, they'll point in slightly different directions, right? One might be perpendicular to the light beam, while the other is at an angle. That's because the surface curves between them. Eratosthenes realized that if he could measure the angle of the sun at two different locations at the same moment, he could calculate the curvature of the Earth between those points. And if he knew the distance between those 2 points, he could calculate the entire circumference. Here's how it works mathematically. In Cyrene, at noon on the summer solstice, the sun is directly overhead. The angle is 0 degrees. A vertical stick casts no shadow. In Alexandria, at the same moment, a vertical stick does cast a shadow. By measuring the length of the shadow and the height of the stick, you can calculate the angle of the sun from vertical. This is basic trigonometry, the kind that surveyors and architects had been using for centuries. Eratosthenes measured this angle and found it to be 1/50th of a circle. Now, a full circle is 360 degrees, so 1/50th of a circle is 7 degrees and 12 minutes of arc, or 7.2 degrees. Here's the crucial insight. This angle, the difference in sun angle between Alexandria and Cyrene, is the same as the angle at the center of the Earth between the 2 cities. This is a property of parallel lines cut by a transversal, which any Greek geometer would know. Think about our orange again. If 2 toothpicks on the surface are at different angles relative to the incoming light, that's because they're at different positions on the sphere, separated by an angle measured from the center of the orange. So Eratosthenes now knows that Alexandria and Cyrene are separated by an angle of 1/50th of a circle measured from the Earth's center. Therefore, the distance between Alexandria and Cyrene represents 1/50th of the Earth's total circumference. If the distance between the cities is, say, 5,000 stadia, then the full circumference must be 50 times 5,000, which equals 250,000 stadia. That's it. That's the whole method. Measure the shadow angle, measure the distance between cities, do some basic geometry, calculate the circumference of the Earth. It's so elegant it makes you want to weep. There's no complicated equipment, no advanced mathematics, no experimental apparatus that takes years to build. Just a stick, its shadow, a well, some distance measurements, and geometric reasoning that any educated Greek could follow. Of course, the devil is in the details. First, how do you know that the sun is directly overhead in Cyrene at noon on the summer solstice? Eratosthenes relied on reports, probably from travelers, merchants, or garrison soldiers. The summer solstice was a well-known date. It's when the sun reaches its northernmost point in the sky, and the phenomenon of the shadowless well was striking enough that people noticed and talked about it. Second, how do you measure the angle in Alexandria precisely? Eratosthenes used a gnomon, a vertical stick or column, and measured the shadow it cast at noon on the summer solstice. The ratio of the shadow length to the height of the gnomon gives you the tangent of the angle. From that, you can calculate the angle itself. Greek mathematicians had tables for this kind of thing, or you could use geometric constructions. The measurement wasn't digital readout precise, but it was good enough. Third, and this is the big one, how do you measure the distance between Alexandria and Cyrene? Now, the cities are about 800 kilometers apart, directly north-south of each other along the Nile. 800 kilometers is a long way, and ancient people didn't have odometers or GPS. So, how did Eratosthenes determine the distance? The traditional story is that he used the reports of bematists, professional pacers, employed by the Ptolemaic government to measure distances. These were people trained to walk with consistent stride lengths, counting their steps to measure distances for military and administrative purposes. The Ptolemies, like any government, needed to know how far apart their cities were for tax collection, troop movements, and trade route planning. Another possibility is that he used travel times. If caravans regularly took a certain number of days to travel between the cities, and you knew their average speed, you could calculate the distance. Multiple methods could be cross-referenced. According to various ancient sources, Eratosthenes determined the distance to be 5,000 stadia. Some accounts say 5,750. The exact number is debated by scholars, partly because we're not entirely sure which stadion he was using, but 5,000 is the number most commonly cited. So, 5,000 stadia times 50 equals 250,000 stadia for the Earth's circumference. Now, how close was he? This is where we run into the stadian problem again. Different Greek city-states used different stadia. The Attic stadion was about 185 meters. The Egyptian stadion was about 157 and 5/10 meters. The Ptolemaic stadion might have been different still. If Eratosthenes used the Attic stadion, his calculation gives a circumference of about 46,250 kilometers. The actual circumference of the Earth at the equator is about 40,075 kilometers. That makes him about 15% too high, not perfect, but pretty damn good. If he used a shorter stadion, say, the one that makes his calculation come out to about 39,390 kilometers, then he was within 2% of the correct value. That's extraordinary. That's modern surveyor accurate using ancient tools and methods. Even if we assume the less favorable stadion and the larger error, he was closer than anyone else would be for almost 2,000 years. Columbus, in 1492, thought the Earth was much smaller than Eratosthenes, had calculated one reason he thought he could sail to Asia by going west. If Columbus had believed Eratosthenes, he might have realized the journey was impossible with the ships and supplies of his day. Ironically, Eratosthenes' better measurement might have prevented the European discovery of the Americas, at least for a while. But here's what really matters. Eratosthenes didn't just guess. He didn't just estimate. He conducted a reproducible experiment based on geometric principles. He showed that you could measure the cosmos with reason and observation. That's science. That's the scientific method in action, 2,000 years before we gave it that name. Chapter 4. The Man Behind the Measurement. So, who was this Eratosthenes as a person? What do we know about the man beyond his mathematics? Frustratingly, not as much as we'd like. He lived over 2,000 years ago, and most of his writings haven't survived. We know about his work through references in other ancient authors, people like Strabo, Ptolemy, not the king, the astronomer from a few centuries later, Cleomedes, and others who cited him. It's like trying to reconstruct someone's personality from their tweets being quoted by other people. You get glimpses, but not the full picture. But here's what we do know. Eratosthenes was respected in his time, even with that beta nickname. He was chosen to head the Great Library, which means Ptolemy III trusted his judgment and scholarship. He tutored the king's son. He corresponded with other scholars across the Mediterranean. His works were widely read and cited. He was a central figure in the intellectual life of Alexandria for decades. The beta nickname Victau Alpha in Greek seems to have stuck, though. Some sources suggest it was actually affectionate, a recognition that he was excellent at everything, even if not the single greatest specialist in any field. But others suggest there was some jealousy involved. Imagine being good at poetry, mathematics, geography, astronomy, philosophy, and history, and your colleague's response is, "Yeah, but you're not the best at any of them." It's the ancient world's version of Jack of all trades, master of none. Except that phrase is actually misquoted. The full saying is, Jack of all trades, master of none, but oftentimes better than master of one, which actually fits Eratosthenes perfectly. His ability to synthesize knowledge across disciplines is what enabled his great achievements. A pure mathematician might not have thought to apply geometry to geography. A pure geographer might not have had the mathematical skills to work out the calculation. Eratosthenes could do both, and that made all the difference. There's also evidence of his sense of humor. When he invented his sieve for finding prime numbers, he called it a sieve, capo sigma kappa iota nu omicron nu, like you're sifting flour, but you're sifting numbers. That's a dad joke. That's mathematical humor. He knew his stuff was clever and wasn't above making jokes about it. He wrote a treatise called On the Measurement of the Earth that hasn't survived, but we know about it from references. Can you imagine being able to title your book that? not estimating or theorizing about just straight up on the measurement. That takes confidence. In geography, he tried to create accurate maps of the known world. He drew lines of latitude and longitude, primitive versions of what we use today. He tried to standardize geographical knowledge, collecting reports from travelers and trying to figure out what was accurate and what was exaggeration. This was harder than it sounds. Ancient travelers were like modern internet commenters, prone to wild exaggeration. The fish in Persia are this big. There are people in Ethiopia with their faces in their chests. Eratosthenes tried to sift fact from fiction. He also waded into historical chronology, trying to establish accurate dates for events like the Trojan War. He worked out a chronology that dated the fall of Troy to around 1184, before the Common Era, which is surprisingly close to what modern archaeology suggests. If Troy fell at all, that's a whole other debate. Again, he was trying to bring order and accuracy to a field that was full of legends and conflicting accounts. In his later years, he went blind. This was devastating for a scholar whose work depended on reading and observation. Some sources say he stopped eating and died of voluntary starvation at the age of 82 or 83. Others just say he died of old age. Either way, it was around 194 before the Common Era. He lived a long life by ancient standards, and a remarkably productive one. He experienced the height of Ptolemaic Alexandria, worked at the greatest library in the world, made contributions to multiple fields, and measured the earth. Not a bad run for someone who was supposedly always second best. Chapter 5. The Mathematics Explained. Let's dive a bit deeper into the mathematics of what Eratosthenes did, because the beauty is in the details. The fundamental principle is similar triangles and properties of circles. If you've ever studied geometry, you've probably encountered these concepts, but maybe never seen them applied to something as grand as measuring the planet. Imagine the Earth as a perfect sphere. It's actually an oblate spheroid, slightly flattened at the poles, but a sphere is close enough for this purpose. The center of the sphere is the center of the Earth. Now, imagine two lines going from the center of the Earth up to the surface, one to Alexandria and one to Cyrene. These are radii of the Earth. The angle between these two radii, measured at the center of the Earth, is what we want to find. Now, at noon on the summer solstice, the sun is directly overhead at Cyrene. This means a ray of sunlight coming down is exactly aligned with that radius from Earth's center to Cyrene. It's pointing at the center of the Earth, so to speak. At the same moment in Alexandria, the sun isn't directly overhead, it's at an angle. A ray of sunlight coming down makes an angle with the vertical with the radius from Earth's center to Alexandria. But here's the key, the sunlight rays at both locations are parallel to each other because the sun is so far away. Parallel lines have special properties when they intersect other lines. Specifically, if you have two parallel lines, the sun rays at Alexandria and Cyrene, and they're cut by two other lines, the radii from Earth's center to each city, then alternate interior angles are equal. This is a fundamental theorem in geometry, known since Euclid. What this means: the angle that the sun ray makes with the radius at Alexandria is equal to the angle between the two radii measured at Earth's center. This is the crucial geometric insight. So, when Eratosthenes measured the shadow angle in Alexandria, the angle from the vertical, he was directly measuring the angle at Earth's center between Alexandria and Cyrene. He found this angle to be 1/50th of a complete circle. A complete circle is 360 degrees. So 1/50th is 7.2 degrees, or 7 degrees in 12 minutes, in the old degree-minute-second notation. Now, if the angle between 2 points on the surface is 1/50th of a full circle, then the arc distance between them along the surface is 1/50th of the full circumference. That's just the definition of how angles and arc lengths relate in a circle. Arc length equals radius times angle, when the angle is in radians. But more intuitively, if you go 1/50th of the way around a circle, you've traveled 1/50th of the circle's circumference. That's obvious once you think about it. So, If Alexandria and Cyrene are 5,000 stadia apart, and that represents 1/50th of the circumference, then the full circumference is 50 times 5,000 equals 250,000 stadia. The math is actually very simple. The brilliance isn't in the calculation any competent mathematician could multiply 5,000 by 50. The brilliance is in recognizing that this measurement could be made at all, that shadows and wells contained information about the shape of the planet, that local observations could reveal global truths. This is the essence of scientific thinking. The world follows rules, patterns, and those patterns can be discovered through observation and reason. You don't need divine revelation or ancient authority. You need a stick, a shadow, a measuring tape, and a brain. Eratosthenes also did something else clever. He assumed that Alexandria and Cyrene were on the same meridian, the same line of longitude, directly north-south of each other. This simplifies the calculation enormously because you're measuring the distance along a great circle, a path through the center of the sphere. In reality, they're not exactly on the same meridian. Cyrene is about 3 degrees east of Alexandria. But that's close enough that the error introduced is small, especially compared to other uncertainties in the measurement. This raises an interesting point about ancient science. They often made simplifying assumptions that weren't strictly true, but were close enough for the available measurement precision. Modern science does the same thing. We assume air resistance is negligible, or that friction is constant, or that the system is in equilibrium not because these things are exactly true, but because they're close enough and the math becomes manageable. Eratosthenes was practical. He could have tried to account for every tiny variation and complication, but that would require more precise data than he had access to. Instead, he made reasonable assumptions, worked out what could be calculated, and got an answer that was remarkably accurate. That's good science. That's engineering thinking. Perfect is the enemy of good enough, as they say, and Eratosthenes was smart enough to know when good enough was actually pretty damn good. Chapter 6. What came before and after. Eratosthenes didn't work in a vacuum. He was part of a long tradition of Greek natural philosophy and mathematics, and his work both depended on what came before and influenced what came after. Before Eratosthenes, there had been attempts to measure the Earth, but they were less successful. Aristotle, as I mentioned, had estimated the circumference based on various observations, but his figure was too large. Archimedes, who was roughly contemporary with Eratosthenes, they overlapped by about 50 years, mentioned a circumference of 300,000 stadia in one of his works, but it's unclear if this was a measurement or an assumption. What Eratosthenes had that others didn't was the right combination of resources, method, and data. The great library gave him access to reports from across the known world. The Ptolemaic government had administrative records about distances between cities. The theoretical framework, spherical Earth, properties of circles, geometric reasoning was well established. He just had to put it all together. After Eratosthenes, his measurement became the accepted value for the Earth's circumference among educated people in the ancient world. Strabo, the geographer writing about 200 years later, cites Eratosthenes extensively. Ptolemy, the astronomer writing in the 2nd century of the Common Era, used Eratosthenes' figure in his astronomical calculations. But interestingly, not everyone believed him. Posidonius, a philosopher and scientist working around 100 before the Common Era, made his own measurement of the Earth's circumference using a similar method but different cities, Rhodes and Alexandria, and came up with a smaller value about 180,000 stadia. This was wrong, significantly smaller than the true value, but it became popular in certain circles. Strabo preferred Posidonius's value to Eratosthenes, and Ptolemy, in his geography, used a circumference that was too small. This had consequences. When Islamic scholars in the medieval period inherited Greek learning, they got Ptolemy's smaller Earth. When this knowledge filtered back into Europe in the Renaissance, scholars debated which ancient authority was correct. Columbus, famously, believed the smaller estimate. He thought Asia was reachable by sailing west across the Atlantic because he underestimated how big the Earth was. If he'd believed Eratosthenes, he'd have known the journey was impossible. There was no way to carry enough supplies for a ship to sail from Europe to Asia without stops, and there were no stops in between, or so he thought. Columbus lucked out because there were two continents he didn't know about right where he needed them. But in a way, the discovery of the Americas happened because post-Eratosthenes scholars got the size of the Earth wrong. Islamic scholars in the medieval period also tried to measure the Earth. Under Caliph al-Ma'mun in the 9th century, astronomers were sent to the Syrian desert to measure the distance corresponding to a 1-degree change in stellar altitude. They came up with a figure that, converted to modern units, is remarkably close to the true value. This was essentially Eratosthenes' method, but with different reference points and more sophisticated instruments. In the modern era, accurate measurement of the Earth's circumference had to wait for precise surveying techniques and eventually satellite measurements. But the principle Eratosthenes established that you could measure the Earth using geometry and observations remained valid. We just got better tools. Today, we know the Earth's equatorial circumference is about 40,075 kilometers, and the polar circumference, around the poles, is about 40,007 kilometers. The difference is due to the Earth's rotation, which creates a slight bulge at the equator. Eratosthenes couldn't have known about this. His measurement was for the meridional circumference pole to pole, roughly, and he got within a few percent. That's extraordinary. 2,000 years later, with satellites and GPS and laser measurements, we can do better. But not that much better, relatively speaking. Chapter 7. The Philosophy of Measurement. Let's step back for a moment and think about what Eratosthenes really accomplished, philosophically speaking. Humans have always wondered about the world. Where does the sun go at night? What holds up the sky? How big is the Earth? These are natural questions, and every culture has answered them in some way, usually with mythology. The Greeks did something different. Starting around the 6th century, before the Common Era, a few thinkers, people like Thales and Anaximander, started suggesting that the world operates according to natural principles that humans can understand. Not Zeus throws lightning bolts, but lightning is a natural phenomenon with a cause. This was radical. This was the birth of natural philosophy, the ancestor of modern science. But there's a big difference between philosophizing about nature and actually measuring it. You can theorize that the Earth is round, but proving it requires evidence. You can guess at the size of the Earth, but measuring it requires method. Eratosthenes represents a crucial step, the move from qualitative observation to quantitative measurement. He didn't just say, the Earth is round and pretty big. He said, the Earth is round and its circumference is 250,000 stadia. That's a number. That's something you can check, something you can use, something that makes predictions. This is huge. This is what transforms philosophy into science. As Lord Kelvin would say over 2,000 years later, if you cannot measure it, you cannot improve it. Measurement makes knowledge actionable, but there's more. Eratosthenes' measurement also required a leap of faith, not religious faith, but scientific faith. He had to assume that the laws of geometry that work on human scales also work on planetary scales. He had to assume that the Earth really is spherical enough that his calculation would work. He had to assume that the sun really is far enough away that its rays are effectively parallel. These assumptions are all correct, but he couldn't prove them directly. He was extending local knowledge to global scales, using mathematical reasoning to bridge the gap between what he could observe directly and what was too large to see. This is also fundamental to science. The universe is regular. The same rules apply everywhere. If geometry works in Alexandria, it works at the cosmic scale. If light travels in straight lines here, it travels in straight lines everywhere. Philosophers call this the principle of universality or the uniformity of nature. It's an assumption that science requires but cannot prove. We take it on faith, backed by millennia of successful predictions, that the universe doesn't just arbitrarily change its rules in different places or at different scales. Eratosthenes was implicitly embracing this principle, and it worked. The universe played fair. The calculation gave sensible results that matched reality. This might seem obvious to us now, but it wasn't obvious then. Why should the universe be comprehensible to human reason? Why should geometry, an abstract mathematical system, describe physical reality? The ancient Greeks were discovering something profound. The universe is mathematical, and mathematics is the language in which nature speaks. Galileo would later write, "The book of nature is written in the language of mathematics." Eratosthenes was reading that book 2,000 years earlier. There's also something beautiful about the scale of what he did. Here's a man standing on the ground measuring shadows. The most local, immediate, human-scale observation possible. And from this, he reaches out and grasps the size of the entire planet. He connects the intimately small with the incomprehensibly large through pure thought. This is what mathematics does. It lets us transcend our physical limitations. We can't see the curvature of the earth directly. We're too small, too close to the ground. But we can reason about it. We can deduce it. We can measure it indirectly. In a sense, Eratosthenes was the first person to really see the Earth as a planet, as a sphere floating in space. Everyone before him saw the Earth as the ground beneath their feet, the landscape around them. Eratosthenes saw it whole. That's a perspective shift of enormous magnitude. It's worth noting that this perspective, the Earth as a measurable object, a planet in space, wouldn't become common until the space age, when we actually left the planet and looked back at it. The famous blue marble photograph from 1972 gave millions of people the view that Eratosthenes had achieved mathematically 2,000 years earlier. That's the power of mathematics and science. They let you see things you cannot physically see. They extend your senses. They augment your mind. A stick and a shadow become a telescope pointed at the shape of the world itself. Chapter 8. Eratosthenes, the polymath. Let's return to Eratosthenes, the person, and explore his other accomplishments, because focusing only on his measurement of the Earth does him a disservice. He was, after all, nicknamed Beta, because he was excellent at everything, not just geodesy. In geography, his contributions went far beyond measuring the circumference. He essentially created the field as a systematic discipline. Before Eratosthenes, geography was mostly travelers' tales and sailors' reports, useful but unsystematic, full of errors and exaggerations. Eratosthenes tried to create a scientific geography. He divided the known world into geometrical sections, using lines of latitude and longitude. He recognized that these lines should be based on astronomical observations, the position of the sun, the length of day and night, the stars visible at different latitudes, not just arbitrary divisions. He drew maps. These maps haven't survived. We only know about them from descriptions by later authors, but they were apparently quite good for their time. He showed the Mediterranean, North Africa, Europe, and Asia as far as India. He included the Arabian Peninsula, Persia, even reports of lands far to the east that might have been early garbled accounts of China. He knew the maps weren't perfect. He knew he was working with incomplete data. But he also knew that an imperfect map was better than no map, and that future geographers could improve on his work. That's the scientific attitude. Build on what you know, acknowledge what you don't, and invite others to do better. He tried to calculate the distance from the Straits of Gibraltar to India. He tried to figure out how wide the Erythraean Sea, the Indian Ocean, might be. These weren't just idle speculations. They were attempts to create a comprehensive picture of the world's geography. In his work, Geographica, which sadly only survives in fragments quoted by other authors, he discussed the physical features of different regions, the climates, the peoples, their customs. He was doing what we'd now call human geography as well as physical geography. He also debunked a lot of nonsense. Ancient travel literature was full of fantastic tales. Men with dog heads, people with one giant foot they used as an umbrella, tribes of women, warriors, you name it. Eratosthenes was skeptical. He tried to separate reliable reports from obvious fabrications. This made him somewhat unpopular among those who enjoyed a good fantastic tale. Strabo, writing about 200 years later, occasionally criticizes Eratosthenes for being too skeptical, for not believing Homer's account of Odysseus's travels, for insisting that poets weren't reliable geographical sources. Imagine that, insisting that mythology might not be accurate geography. What a killjoy! But Eratosthenes was right to be skeptical. Good scholarship requires distinguishing between what you know, what you think might be true, and what's probably nonsense. That's hard when the person telling you the story is very confident and everyone else seems to believe them. It's easier to just go along with the conventional wisdom. Eratosthenes didn't go along. He questioned, he verified, he cross-referenced. That's what made him a good scientist, even if it made him less fun at parties. In mathematics, beyond the sieve, he worked on what we'd now call number theory. He studied perfect numbers, amicable numbers, and other properties of integers. Some sources suggest he worked on conic sections, the mathematics of ellipses, parabolas, and hyperbolas, though the details are unclear. He also worked on a famous problem called the Delian problem, or the doubling of the cube. The challenge is to construct, using only compass and straight edge, a cube with exactly twice the volume of a given cube. This turns out to be impossible. It requires cube roots, which can't be constructed with only compass and straight edge, but the ancient Greeks didn't know that. Eratosthenes came up with a mechanical device, a kind of sliding frame that could approximate the solution. It wasn't a pure geometric construction, so it didn't really solve the problem as stated, but it was clever and practical. Very Eratosthenes. If you can't solve it the right way, find a different way that works. In astronomy, he measured the tilt of the Earth's axis, the obliquity of the ecliptic, and got a value very close to the modern measurement. This is the angle between the Earth's rotational axis and the perpendicular to its orbital plane, and it's why we have seasons. He calculated it as 11/23 of a right angle, which works out to about 23 degrees and 51 minutes. The modern value is about 23 degrees and 26 minutes. That's remarkably close for measurements made with ancient instruments. He also compiled a star catalog, listing the positions of stars. This was enormously useful for navigation and for tracking the precession of the equinoxes, the slow wobble of Earth's axis over thousands of years. In chronology, the study of historical dates, he tried to establish a reliable timeline of events. This was a huge mess in the ancient world. Different cities had different calendars. Different cultures started their year at different times. Events were dated relative to local rulers or Olympic Games or the founding of cities, and none of these systems talked to each other. Eratosthenes tried to create a universal chronology, at least for the Greek world, dating events consistently. He dated the Trojan War, the founding of various cities, the lives of famous people. This became a standard reference for later historians. Was he always right? No. Historical dating is hard even with modern archaeological methods. But he was systematic, and he showed that it could be done. In poetry and literature, he wrote works that were well regarded in his time. His poem Hermes told the story of the god's birth and early exploits. It was apparently charming and clever, full of wordplay and mythological references. Nothing like it survives, so we can't judge for ourselves, but ancient literary critics spoke well of it. He also wrote works of literary criticism, analyzing Homer and other poets. He argued that poetry should be judged as poetry for its artistry and emotional impact, not as a source of factual information. This seems obvious now, but at the time, many people treated Homer as a historical document. Eratosthenes was more nuanced. Enjoy the poetry, but don't navigate by it. So when we call Eratosthenes a polymath, we're not exaggerating. He really did contribute to multiple fields at a high level. And he did it all while running one of the largest libraries in the world and tutoring royalty. The question is, how? How did he find the time? How did he maintain focus across so many different areas? Part of the answer is probably that these fields weren't as separate in the ancient world as they are now. A scholar was expected to know poetry, mathematics, philosophy, history. They were all part of being an educated person. Specialization is a modern phenomenon, driven by the sheer volume of knowledge in each field. But part of it is probably also that Eratosthenes was just exceptionally talented and driven. He was curious about everything, and he had the resources and freedom to pursue that curiosity. Not many people in history have had that combination. Chapter 9. The Library and its Legacy. We can't talk about Eratosthenes without talking about the Great Library of Alexandria, because his work was enabled by that institution, and his tenure as librarian shaped its golden age. The library, or more accurately, the Mauseon, of which the library was a part, was unlike anything that had existed before. Previous libraries were royal or temple archives, collections of records and religious texts. The Library of Alexandria was different. It aimed to collect all knowledge, from all cultures, in all languages. That was the vision of Ptolemy I and his successors. Alexandria would be the intellectual capital of the world, and the library would be its heart. To make this happen, the Ptolemies threw money at the problem. They paid scribes to copy texts. They paid scholars to translate works from other languages into Greek. They sent agents to acquire books from across the Mediterranean and beyond. The famous story about confiscating books from ships is true. Any ship docking in Alexandria had to surrender its books for copying. The Ptolemies were relentless. By Eratosthenes' time, the collection was enormous. Estimates vary wildly. Some ancient sources claim 700,000 scrolls. Others say 400,000. Still others 500,000. The exact number is unknowable, partly because ancient sources exaggerated, and partly because counting scrolls is tricky. Is a multi-volume work one book or several? Is a scroll with multiple texts one scroll or many? But let's be conservative and say there were at least hundreds of thousands of texts. In a world where each text was hand-copied and expensive, this was an almost unimaginable wealth of knowledge. The Mauseon wasn't just storage, it was a research institution. Scholars lived on site or nearby. They received stipends from the Ptolemaic government. They had access to the collection. They could devote themselves to research and writing without worrying about earning a living. It was the ancient equivalent of the Institute for Advanced Study at Princeton, or CERN, or any modern research institution, but it came first. Nothing like it had existed before. The Mauseon had lecture halls, meeting rooms, botanical gardens, a zoo, an observatory. It was a complete intellectual ecosystem. Scholars from across the Mediterranean came to work there. Greek, Egyptian, Jewish, Persian scholars all contributed. This is where Euclid wrote his Elements, the geometry textbook that would be used for over 2,000 years. This is where Archimedes studied before returning to Syracuse. This is where Apollonius worked on conic sections. This is where Aristarchus proposed that the Earth orbits the Sun, a heliocentric theory that wouldn't be accepted until Copernicus rediscovered it 1,700 years later. And this is where Eratosthenes, as head librarian, oversaw it all. His job was enormous. He had to manage the collection, deciding what to acquire, how to organize it, how to catalog it. Remember, there was no Dewey Decimal System, no ISBN numbers, no standardized cataloging. Every scroll had to be individually assessed and categorized. He had to manage scholars, and scholars are notoriously difficult to manage. They have strong opinions. They quarrel over priority and credit. They want resources for their own projects. Eratosthenes had to keep the peace, allocate space and funding, and somehow keep everyone productive. He had to deal with forgeries and misattributed texts. Ancient booksellers were not above slapping a famous name on a text to increase its value. Lost works of Aristotle appeared regularly, most of them fake. Eratosthenes had to use his literary and historical knowledge to authenticate texts, and he had to do his own research and writing on top of all this. The measurement of the earth, the geographical work, the mathematics, the poetry, all of this was done while running the library. It's no wonder he was nicknamed Beta. Being the best at any one thing would require devoting all your time to it. Eratosthenes was dividing his attention across administration, research, writing, teaching, and more. That he achieved as much as he did is remarkable. The library's fate is one of history's great tragedies. It didn't survive. We're not even entirely sure how or when it was destroyed. The traditional story is that Julius Caesar accidentally burned it in 48, before the Common Era, when his troops set fire to ships in the harbor and the fire spread. But that's probably not the whole story. More likely, the library declined gradually over centuries. Funding dried up as the Ptolemaic kingdom weakened and was eventually absorbed by Rome. Political instability made Alexandria a less attractive destination for scholars. The collection was neglected, dispersed, damaged by multiple fires and conflicts. By the time of the Islamic conquest of Egypt in the 7th century of the Common Era, the library as an institution was long gone. The famous story of Caliph Omar ordering its destruction. If the books agree with the Quran, they are redundant. If they disagree, they are heretical. In either case, the Quran's of ours, that nuisance, burn them is almost certainly a myth, invented centuries later. What's tragic isn't any single act of destruction. It's the slow loss of irreplaceable knowledge. Most of the works in the library are simply gone. We have a few texts that were copied and recopied and survived. We have references and quotes in other works, but the vast majority is lost forever. Of Eratosthenes' own writings we have fragments and summaries, but not the original texts. His Geographica is gone. His poetry is gone. His mathematical treatises are gone. We know about them because later authors quoted or summarized them, but we can't read Eratosthenes in his own words. It's like knowing that Shakespeare wrote amazing plays but only having reviews and summaries, not the plays themselves. We know Eratosthenes was brilliant because everyone said so, but we can't fully appreciate his genius because his work is lost. This is why the destruction of the library matters. It's not just that a building burned, it's that human knowledge was lost, ideas and insights that took genius to create and can never be recreated. And yet, some things survive. Eratosthenes' method for measuring the earth survives because it was simple and elegant enough that others could describe it. His sieve survives because it's useful and easy to explain. His key insights survive because they became part of the foundation of later science. In that sense, the library succeeded. It preserved and transmitted knowledge, even though the institution itself didn't last. The knowledge spread throughout the Mediterranean world and beyond. When the library fell, its intellectual legacy had already propagated elsewhere. Eratosthenes' work, in particular, influenced every geographer and astronomer who came after. His measurement was cited for centuries. His methods were emulated. His vision of a scientific geography shaped the field. The library died, but what it enabled lived on. Chapter 10. Legacy and Modern Relevance. So here we are, over 2,000 years later. Why should we care about Eratosthenes? What does his work mean for us today? The obvious answer is historical. He's an important figure in the history of science, and understanding the history of science helps us understand how we came to know what we know. That's valuable, but it's not the whole story. The deeper answer is that Eratosthenes exemplifies a way of thinking that remains relevant and powerful. The scientific method, the belief that the world is comprehensible, and the courage to measure and question rather than simply accept. We live in a world saturated with information and technology, much of it based on science that Eratosthenes helped pioneer. GPS satellites orbiting Earth and calculating positions based on geometric principles. That's Eratosthenes' intellectual descendant. Weather prediction models treating Earth as a sphere with latitude and longitude? Same lineage. The entire field of Earth science? It stands on foundations that Eratosthenes helped lay. But beyond specific applications, there's the method. Eratosthenes showed that you could answer big questions by breaking them down into measurable components. You couldn't measure the Earth directly, but you could measure shadows. You couldn't observe the curvature directly, but you could infer it from differences in sun angle. You couldn't test your result by traveling around the world, but you could check whether the calculation made sense based on other observations. This is how science works. You observe, you measure, you reason, you check. You don't just trust authority or tradition. You verify, you test, you demand evidence. In an age of misinformation, this matters more than ever. We're bombarded with claims and counterclaims. How do you know what's true? Eratosthenes would say, look at the evidence. Check the measurements. See if the logic holds up. Don't be satisfied with everyone says so, or it's obvious, or trust me. Eratosthenes also exemplifies intellectual courage. He was willing to trust his own reasoning even though it led to conclusions that must have seemed bizarre to many people. The Earth is 250,000 stadia around? That's enormous. How can you possibly know that from measuring a shadow? But he did know it because the mathematics was sound and the observations were careful. He trusted reason and evidence over intuition and convention. We need that courage today. Climate science, for example, tells us uncomfortable truths based on measurements and models. Some people reject it because the conclusions are inconvenient or counterintuitive. Eratosthenes would say, look at the data, check the reasoning. If the measurements are sound and the logic is valid, accept the conclusion even if you don't like it. Or consider the current debates over AI, genetic engineering, quantum computing. These are areas where what's possible is changing rapidly, where old assumptions might not hold, where we need to think carefully about measurements, evidence, and implications. Eratosthenes reminds us that big questions can be answered, that careful thought and measurement can reveal truths about the world, and that doing so requires both technical skill and intellectual honesty. There's also the interdisciplinary aspect. Eratosthenes didn't stay in his lane. He worked across mathematics, geography, astronomy, poetry, history. He saw connections between fields that others missed. His measurement of the Earth required bringing together geometry, observational astronomy, geographic knowledge, and administrative records. Today, we're rediscovering the value of interdisciplinary work. The biggest problems, climate change, pandemics, AI safety, sustainable energy, don't fit neatly into single disciplines. They require people who can think across boundaries, who can apply insights from one field to problems in another. Eratosthenes was that kind of thinker. Maybe being second best at multiple things really is better than being the absolute best at just one, especially when the best work requires synthesis. Finally, there's something inspiring about Eratosthenes' story. He was one person, working with simple tools, addressing a question that seemed unanswerable, and he answered it. He measured the Earth. That's the kind of achievement that makes you think, what else might be possible? What other seemingly impossible questions might yield to clever methods and careful thought? Every time someone uses a simple, elegant method to solve a complex problem, they're channeling Eratosthenes. Every time someone trusts in the power of reason and measurement to reveal truth, they're following his example. The physicist Richard Feynman once said, "What I cannot create, I do not understand." Eratosthenes would probably agree, with a modification. What I cannot measure, I do not truly know. Measurement makes knowledge concrete, testable, useful. In our modern world, we measure everything: economic growth, social media engagement, carbon emissions, vaccine efficacy, quantum entanglement. We're a civilization of measurers, and Eratosthenes is one of our ancestors. But we should also remember his humility. He knew his measurements weren't perfect. He knew future scholars might improve on his work. He wasn't trying to have the final word. He was contributing to an ongoing project of understanding the world. That's the scientific attitude. We build on what came before, we do the best we can with available tools and knowledge, and we invite others to improve on our work. Science is collaborative across time, a conversation spanning millennia. Eratosthenes is still part of that conversation. We still cite him, still teach his method, still admire his achievement. Not bad for someone who's been dead for over 2,000 years. Chapter 11. The bigger picture. Let's zoom out even further and think about what Eratosthenes' work represents in the grand sweep of human intellectual history. Humans have been looking up at the sky, wondering about the cosmos, trying to make sense of the world for as long as we've been human. Every culture has cosmologies, origin stories, explanations for why things are the way they are. But somewhere around the 6th century, before the Common Era in ancient Greece, something shifted. A few thinkers started suggesting that natural phenomena might have natural explanations. Not the gods are angry, but this happens because of that. This was the birth of rational inquiry, the beginning of the long process that would eventually become science. It wasn't a sudden revolution, it took centuries to develop, and it happened in fits and starts with plenty of backsliding. But it was a real shift in how humans approached questions about the world. Eratosthenes stands at a crucial point in this development. By his time, the basic framework was in place. Reason can reveal truth. Observation matters. Mathematics describes reality. But translating this framework into actual concrete knowledge about the world that required people like Eratosthenes actually doing it. Measuring the Earth wasn't just an interesting factoid. It was a proof of concept. It showed that you really could use human reason and careful observation to learn things about the cosmos that were not obvious, that couldn't be perceived directly, that seemed beyond human ken. Before Eratosthenes, you might believe in principle that the world was comprehensible. After Eratosthenes, you had evidence. Here's a thing we didn't know. And now we know it, and we know it with precision. This matters because knowledge builds on knowledge. Once you know the size of the Earth, you can start figuring out other things. How far away is the moon, the sun? How do planetary orbits work? Each question answered opens up new questions. Each measurement enables new calculations. Aristarchus of Samos, working around the same time as Eratosthenes, tried to measure the distance to the sun and moon using geometric methods. His measurements weren't very accurate. The angles involved are hard to measure precisely with ancient instruments, but the method was sound. He showed it could be done. Hipparchus, working about a century after Eratosthenes, used careful astronomical observations to calculate the distance to the moon with impressive accuracy. He also discovered the precession of the equinoxes and compiled detailed star catalogues. Ptolemy, in the 2nd century of the Common Era, synthesized centuries of Greek astronomy into his Almagest, a comprehensive model of the cosmos. It was geocentric and ultimately wrong in important ways, but it was mathematically sophisticated and made accurate predictions. All of this work built on the foundations that people like Eratosthenes laid. The measurement of the Earth was a stepping stone to measuring the solar system, which was a stepping stone to understanding orbital mechanics, which was a stepping stone to space travel. It's a direct line from Eratosthenes measuring shadows in Alexandria to the Apollo program landing on the moon. The specific methods evolved dramatically, but the fundamental approach, careful measurement, mathematical reasoning, building on previous knowledge, remained the same. This is the cumulative nature of science. Each generation builds on what came before. Some ideas are dead ends and get abandoned. Some are correct and get refined. But overall, there's progress. We know more about the universe now than we did a century ago, or a millennium ago, or 2 millennia ago. Eratosthenes contributed a brick to this enormous edifice of human knowledge. It's a foundational brick, one that others built upon, but it's still just one brick among billions. And yet, it's important. Without that brick, the structure might have taken longer to build or been less stable. Here's another way to think about it. Eratosthenes showed that scale doesn't matter. Human minds, human reasoning, human mathematics can grapple with questions at any scale. We're tiny creatures on the surface of a planet, but we can figure out the size of that planet. We can, through thought alone, transcend our physical limitations. This is profound. It suggests that there's no question too big for human inquiry, no scale too vast, no mystery too deep. If we're clever enough, patient enough, careful enough, we can figure it out. Now, that doesn't mean we know everything or ever will. There are limits to what can be known. Either in principle, quantum mechanics tells us some things are fundamentally uncertain, or in practice, some questions might be answerable in theory, but impossibly difficult in practice. But the attitude Eratosthenes embodied, that big questions can have answers, that those answers can be found through reason and observation, that's the engine that drives scientific progress. Think about the questions we've answered since Eratosthenes. What are stars made of? How old is the Earth? How do species evolve? What is matter made of? How does the brain work? What happened in the first moments after the Big Bang? Every single one of these seemed impossible or even meaningless before someone figured out how to actually investigate it. And the investigations always follow the same pattern. Break the big question into smaller questions. Find ways to measure and observe. Use mathematics and logic to connect observations to conclusions. That's the method Eratosthenes exemplified. And it works. It's given us modern medicine, technology, our understanding of the cosmos. It's not perfect. Science makes mistakes, takes wrong turns, sometimes gets things embarrassingly wrong. But it's self-correcting, and over time, it converges on truth. Eratosthenes was one of the early practitioners of this method. He showed it could work on grand scales. And for that, he deserves to be remembered not just as a historical curiosity, but as a founding figure in humanity's greatest collective project, understanding the universe. Chapter 12, Reflections on Beta. Let's return to that nickname, Beta. The second letter, second best at everything. There's something almost poignant about it. Here's a man who measured the Earth, invented geographical science, contributed to mathematics, wrote poetry, ran the greatest library in the world, and his contemporaries summed him up as pretty good at everything, best at nothing. It raises the question, what were they comparing him to? Who was the alpha in each field? In mathematics, they probably thought Archimedes was better. And to be fair, Archimedes was extraordinary, a once-in-a-millennium genius who discovered calculus-like methods 2,000 years before Newton and Leibniz, who understood centers of mass and buoyancy, who built war machines that held off Roman armies. If you're being compared to Archimedes and come in second, you're in pretty good company. In poetry, maybe they preferred Callimachus, who was also associated with the library and was known for elegant, learned verse. In geography, maybe someone thought Dicarchus was more important for earlier work on the shape of the Earth. But here's the thing. We remember Eratosthenes. We still teach his methods. His name is attached to lasting contributions in multiple fields. The people who supposedly beat him in specific areas. Some of them are barely remembered except by specialists. Being the absolute best at one thing is great if you want fame in that field. But being excellent at multiple things, that might have more lasting impact. Because the really important breakthroughs often come at the intersections of fields, where insights from one domain can be applied to problems in another. Eratosthenes' measurement of the Earth required geography, mathematics, astronomy, and access to administrative records. A pure mathematician might not have thought to attempt it. A pure geographer might not have had the mathematical skills to work it out. Eratosthenes could do both, and that made all the difference. In the modern world, We often overvalue specialization. We want people to pick a lane, become experts in one narrow area, go deep rather than broad. There's value in that. You can't master everything, and some problems require deep expertise. But there's also value in the Eratosthenes approach. Be competent in multiple areas, look for connections, apply insights from one field to another. Some of the most interesting work in science today happens at the boundaries. Bioinformatics, neuroscience, quantum computing, climate modeling. These fields require people who can speak multiple disciplinary languages. Maybe beta wasn't an insult. Maybe it was an observation that Eratosthenes didn't fit neatly into existing categories. He was interdisciplinary before the term existed. He was a systems thinker. He saw the big picture. There's also something to be said for the personality type that Eratosthenes seems to have had. He doesn't come across as an egomaniac or a glory seeker. He wasn't trying to be the absolute best to prove something to himself or others. He was curious. He wanted to know things. He wanted to solve problems. The recognition was secondary. Compare that to some other famous ancient scholars. Archimedes allegedly said, "Give me a place to stand and a lever long enough, and I will move the world." That's a pretty bold claim. Eratosthenes, as far as we know, just quietly did his work, wrote his books, ran the library, and measured the earth. No drama, no grand pronouncements, just solid scholarship. There's something admirable about that. In an age of self-promotion and personal brands, Eratosthenes reminds us that good work speaks for itself. You don't need to be the loudest voice in the room or the most self-assured. You just need to be careful, thorough, and honest. And maybe that's why his work has lasted. It wasn't built on personality or rhetoric or force of will. It was built on solid method, careful measurement, and clear reasoning. Those things endure. So perhaps we should reclaim beta as a badge of honor. Being second best at many things means you're excellent across the board. It means you can see connections others miss. It means you're not locked into one way of thinking. In Eratosthenes' case, being beta meant he could measure the earth, advance mathematics, create geography as a discipline, write poetry, manage a great library, and teach princes. Not a bad resume for someone who was supposedly only second best. The next time someone tells you that you need to pick one thing and focus on it exclusively, think of Eratosthenes. Sometimes the greatest achievements come from bringing together multiple kinds of knowledge. Sometimes being good at many things is better than being the absolute best at one. And sometimes the second best person in multiple fields accomplishes more than the first best person in any single field. That's the real lesson of Eratosthenes. Intellectual breadth matters. Curiosity matters. Being willing to tackle big questions matters. And sometimes, the person who measures the earth is the person nobody expected to do it. Good night.
And in case you've enjoyed our evening talk so much, and still might be awake, here is another educational video for you.